But what would be really nice is if we didn't need to reduce the nitro group at all, because if you think about it, we're putting in a lot of reducing equivalents to take this oxidation state down. That's putting a lot of energy into the substrate, and really, in environmental terms, it's quite a redox inefficient route, and as modern chemists we should be trying to make our synthesis routes green and efficient as well as high yielding and effective. Somebody else also seems to have had this thought, and so the final route I'll go through is this paper from Synthetic Communications. It describes the production of phenethylamines from dihydrocinamic acid starting materials. And so a dihydrocinamic acid is just a reduced version of the parent compound cinnamic acid. This is the commercially available starting material, but I think it's nice to be consistent and also consider how we might derive the starting material from our benzaldehyde that we've been using for the previous routes. And it turns out that you can condense a benzaldehyde with this reagent here, Meldrum's acid, in the presence of triethylamine and formic acid, and in one reaction pot go straight to the dihydrocinamic acid that we need to start the final mescaline synthesis. And this compound, Meldrum's acid, it's nucleophilic at carbon, and you can see it's sort of made from malonic acid, as if an acetone molecule had been captured across those two oxygens there. So it's nucleophilic at this position, it's a carbon nucleophile. So what's happening in this reaction is the enol of Meldrum's acid is condensing with the aldehyde to give us an intermediate adduct that looks something like this. And because all of this system is held together in a cyclic arrangement, it can decompose in a pericyclic process. The electrons flow around the ring, and there's an extrusion of both carbon dioxide and acetone, and the product is this ketene. And there's water present either in the reaction mixture or the workup that can attack the electrophilic center at the middle of the ketene. The electrons temporarily flowing up onto the oxygen and generating this enolized carboxylate, and that can break down by ejection of the beta hydroxy group, which picks up a proton as it leaves, and the product is this cinnamic acid. And so now we have this cinnamic acid, but I also mentioned that the reaction mixture contains triethylamine and formic acid, and like we saw before, the formic acid can break down, contribute hydride reducing equivalents, and reduce out the double bond of the cinnamic acid, and the eventual product is this dihydrocinamic acid, which is the required starting material for the final step of the mescaline synthesis. Okay, final step. The author uses this dihydrocinamic acid to carry out a Curtius rearrangement. And so the first thing that happens is he condenses the dihydrocinamic acid with isobutyl chloroformate, and the product is this mixed anhydride. That mixed anhydride is a lot more electrophilic than the carboxylate at this carbon, and so it can be reacted with sodium azide, and the azide nucleophile comes in and just displaces this other carboxylate as the leaving group, and an acyl azide is the product. And you could go directly from the acid to the acyl azide using hydrozoic acid, but that's bad news because it's a highly unstable and explosive compound. It's best avoided. So this sort of two-step way lets you activate the ester and then react it with a nucleophile. And so if we redraw the acyl azide in full, the functional group has a couple of resonance forms. So depending on how you draw your arrows, the negative charge is either localized on the terminal nitrogen or this internal nitrogen. And you might be thinking that this system looks a lot like that alpha diazoketone we saw way back at the beginning of the video, and indeed it has the same sort of reactivity. So this N2 group here can just take the electrons from that bond, leave as gaseous dinitrogen, and whereas previously we were left with a carbene, now we're left with the nitrogen equivalent, which is called a nitrene. It does the same sort of thing, pushes its electrons to make a bond next door. This time the alkyl group migrates across, and the result of that rearrangement is this isocyanate. And much like a ketene, the isocyanate is very electrophilic at the central carbon, so it can suffer attack by various nucleophiles like water, and in reality the author treats his isocyanate with a dilute solution of sulfuric acid. And so after the addition of water, a carbamate is formed, and then the carbamate isn't particularly stable. It can be attacked by a further molecule of water, and it's hydrolyzed to give you the product, which is the free terminal amine, or in our case mescaline, so that completes the final synthesis. And so, in conclusion, we've seen 3 different ways to make mescaline. We've seen a very classical route that proceeded via the Arndt-Eichstädt homologation of an alpha-diazo ketone, followed by reduction of the terminal amide to form mescaline. We've seen Alexander Shulgin's preferred route of using the Henry condensation to produce a nitrostyrene, and we've seen some nice modern chemistry where a dihydrocyanic acid was converted to an acyl azide that underwent the Curtius rearrangement. And these are just some of the ways that you might make this particularly interesting phenethylamine product.